Good afternoon, folks. Myself, Anindo from Lyft, and my colleague Han Wang. He is also a Lyft software engineer, a senior staff engineer. So we'll be talking about Ray on Kubernetes today. Especially Ray is a new framework, and Lyft is a Kubernetes house. So we try to merge both of these technologies and how we work on it. So Han will talk about the first half, and then I will take care about the demo sessions. Han.
Hello, everyone. Welcome. Today, Anindo and I will talk about the distributed machine learning with Ray on Kubernetes inside Lyft. Both of us work in the machine learning platform team of Lyft. Our focus is on the large-scale distributed systems for machine learning. Here is today's agenda. I will talk about the pain points and the design principles of the machine learning platform of Lyft. And then Anindo is going to dive deep into the Ray integration. So inside Lyft, most of our business decisions are empowered by machine learning models. As the machine learning platform team, we work with all the practitioners inside the company. And here are the common things that we learned from the practitioners. First of all, we notice we have very good engineers and scientists. They write nice code. But most of the code is just to run locally. They don't know how to scale out. We see another group of people who has some knowledge of a certain distributed framework, and then they try to scale out. But it's not very successful. Their code becomes convoluted and unmanageable very quickly, and the scalability is not really very good. And another problem is single vendor locking. This is not only a technical problem, but also a mindset problem. Think about that. We use Spark widely inside the company. So a lot of people, their mindset is on Spark. They try to build the end-to-end machine learning pipeline all on Spark. Fairly speaking, Spark is pretty good on most parts of a machine learning pipeline. But for example, one thing it cannot do very well, that is the training step. So the problem is they have very scalable pre-processing, post-processing, but they don't know how to scale out their training process. And the cost of iteration is another big pain point. So as the data size increase, as the model complexity increase, the time and cost will increase drastically. How do they handle that? How do they do multi-step iterations? The last but not the least, we notice that following good practices sometimes are penalized. For example, if I want to add unit test to the pipeline, what if I want to do hyperparameter tuning? What if I want to do data validation? All of those good practices, they will require huge amount of effort. And by doing so, sometimes it's very hard to justify from the business perspective. So practically speaking, we notice people tend to skip those steps and to ship models directly, which is obviously very risky. So based on these pain points, here are our design principles for our machine learning platform. First of all, it must be very easy to use, and it must be very seamless to use, no matter which kind of solution you are using. We take the layered cake approach. So instead of one layer of abstraction, we have multiple layers of abstractions. So for common use cases and common users, they commonly just need to access the top level abstraction, which is mostly one-liner, which you will see in our demo in the later sections. And for the advanced use cases, they will be able to access the full feature of the frameworks provide. The second thing, we want to abstract away the concern of scale and vendor lock-in. We want users to focus on their core business logic and computing logic without too much concern about scalability and how to adapt to a certain computing framework. We will handle that through our abstraction layers. Enabling fast iteration. I think this is very important because enabling fast iteration, it will save a lot of time and also it will save huge amount of cost for the company. So in order to do that, we must provide a collection of utility functions that is very easy to use, but under the hood, it will fully utilize the distributed system that we have. So actually, increasing the utilization of the whole cluster is a very effective way to accelerate the iterations. And the last but not the least, we want to make following good practices to be rewarding, right? So what we do is we try to provide the most reasonable interfaces and components that people can use directly to do their job. For example, for hyperparameter tuning, we have very simple interfaces for them to interact with any type of distributed systems. For data validation, we have the well-defined interface for them to directly invoke the validation steps. So here is an overview of the Lyft distributed environment, the ecosystem. As you can see in each stack, there are competing solutions, right? But for us, we don't see them to compete with each other. Instead, we think they are complementary to each other. The key is that the abstraction must be right. We must define the most reasonable abstraction so that people can use them freely. People can switch between them freely. So in that way, people can have more options without a lot of frictions. So now I will hand it off to Anindo to dive deep into the Ray integration. Thank you.
Thank you, Han. So to start with, Lyft runs on AWS, and we do not use EC2 directly. We use all K8s instances on top of EC2. So Lyft is an AWS on K8s house. So how does it work? So it's a schematic diagram. Due to the brevity of time, I will keep it short. I can take questions later after this talk. So how does it work? So we have a function called with K8s Ray. We use that function, and I will demo it in a bit. So we submit a Ray cluster job to the Kubernetes API using the Ray cluster operators. And we also have the EFS mounted on each of the operators so that we can have a shared volumes shared across all the workers or Ray actor nodes. This is the same principle we follow with Spark. We just extended Spark on Kubernetes to Ray on Kubernetes, and we have the same infrastructure API for Spark as well. I will show you in a bit. So how does a scientist create a Ray cluster? It's just this one line of code with K8s Ray. That's it. And then they have to mention two parameters, the configuration instances, and whether I want the Ray dashboard or not. So what does this number 4818G stand for? 4 means I want 4 nodes, 8 means I want 8 CPUs per node, and 1 means I want 1 GPU per node, and 8G means I want 8 GB of RAM per CPU in a node. So 4 letters and 1 cluster. And inside that, you do the entire processing, some method.remote, that's it, done. So how can I monitor? We have a Ray dashboard. We also create a Ray dashboard on the fly. We create the ingress. The dashboard is already created. We create the ingress to that service and expose it. How did we come to this idea? So in our last Databricks talk, we had a talk in Databricks also. So for any machine learning workflow, there are primarily 4 steps: pre-processing, training, saving the model, and then post-processing, which is most likely inference. So how we do that in Lyft? As Han was mentioning that, here we are not competing against each other. Ray is powerful for something, Spark is powerful for something. We want to take the advantage of both of them. So the abstraction is from Lyft distributed. So in the first cell, you can see pre-processing. We are using a Spark cluster. We want a 16 nodes, 16 CPU machines with 4 GB RAMs for each executor. We read from a certain data set and apply a transform function. Once the pre-processing is done, what's next? We want training. So Spark doesn't support light GBM distributed training that well. So Ray has a good support for that. So we introduce Ray here on the second step. Do the training on Ray. Once the pre-processing is done, do the training on Ray. So we call the light GBM remote method on the S3 dataset and call the Ray light GBM training. Third step, pretty simple and straightforward, save the model. Once you save it, what do? You do post-processing. Do you want to scale up the post-processing? If yes, use Spark again. So load the model from that saved path, load your test data, and do again a transform, the third line, transform test data and run the predict method on top of it. So there are many more technical details. We do not have time to go into too much of it, but this is a gist and synopsis that 4 steps in the entire machine learning workflow being abstracted with k8s, functions, and everything is running on Kubernetes. And this Lyft distributed is our own framework that we have built in-house. And it comes from Fugue. Fugue is an open source framework. Han is the creator of that framework. And Lyft distributed is heavily inspired by Fugue, and it uses Fugue directly. And we have some more extra wrappers specifically for Lyft. But the main driving engine is the Fugue. Okay, so we talked a lot, talked about theory, showed some codes, nice looking red, blue color, green slides. Does it really work? So let's have a look at the demo and how we do it. So this is a demo of
the first example I want to talk about
of a PyTorch Lightning job that we want to use Ray to distribute it. And I will show another notebook later after this demo. So let's focus on this PyTorch Lightning demo first and see how it works.
Is an inference example. This is a typical piece of code to make inference on a local data frame. The question is, how can we scale out this inference logic? Inside the Lyft, machine learning practitioners often use the Fugue transform to do this type of job. The transform function can take in a path or a data frame as the input. And then we can specify the computing logic, infer. And optionally, we can specify the save path. If this is specified, the output will be directly written into this file location. The interesting part is engine and engine conf. This is highly customized inside Lyft machine learning platform. If you specify this to be Ray, then we will spawn an ephemeral Ray cluster on top of Kubernetes just for this transformation. Before or after this transform, that cluster does not exist. And the size is specified by this simplified expression. We want 16 instances, 8 CPUs for each instance, and 4 gig for each CPU. So that is 32 gig of memory for each instance. This design totally separates the concern of the distributed system and the core computing logic. We want users' computing logic to be framework agnostic and scale agnostic. So actually in this example, if we want to change the computing backend from Ray to Spark, the only thing we need to change is this engine parameter. If we change this to Spark, and then the whole transformation logic will happen on an ephemeral Spark cluster. The second example I want to talk about is training. So look at this piece of code, which is the standard way to train a PyTorch lightning model. The question is, how can we scale out this training process? So Ray has made it very simple. And inside Lyft, we have made it even simpler. Let's take a look at the example. So what we need to do is just to use this utility function to create an ephemeral Ray cluster. The expression is the same as before. And within this context, we just move in these 2 lines of code. The only thing we add is this strategy equal to Ray. This will tell the system that we will use Ray's PyTorch lightning strategy, and we will also pick up the cluster information from the context, so users don't have to manually instantiate that Ray strategy. So with this setting, this training process can fully utilize all the CPUs of this ephemeral Ray cluster. Now the question is, what if we want to use GPUs? So actually, the only thing we need to change is from 8 to 8 and 1. That is to tell the system, for each instance, we want 8 CPUs and 1 GPU. So with this setting, this strategy will be able to pick up the GPU information and to move the whole training onto the 16 GPUs.
Okay, so this was a short demo, like how we integrate PyTorch Lightning with Ray, and that is also, it's abstracted. So the integration is happening under the hood, and also you can switch between Spark and Ray just with a configuration. So we saw a video of the demo, but we actually want to get into the real meat, how it works in Kubernetes. So how do you spawn up clusters? So I have created a notebook here for Ray Summit, and I will try to attempt a more riskier demo now. It's a live. Oh, it's a live cluster creation demo. Let's see if the demo gods are with me. Okay, so I have my command cell up. So I will start watching for the pods. So what we are trying to do, as I mentioned, it's a one-line step for us to create clusters. This cluster is doing nothing, just sleeping. So I want to create 2 nodes, 2 CPUs cluster. Can I do that? So let's go back to the Ray dashboard. The Kubernetes dashboard. So there is only one pod, the notebook which I'm running. Nothing is there. So I try to attempt to create a cluster. So you can see as I try to spin up a cluster, so I see that the Ray head has come up, and I'm still waiting for the worker. And as I speak, the workers are also coming up. So I ask for two extra workers, so I am getting 2 nodes. And then also, I'm really actually spawning up the cluster. So I have watched it, and I can see the state has transitioned. So this cluster did nothing but just to sleep. So the whole point of showing this script was to show how easy for the scientists and researchers to work with the cluster. They just don't need to know anything underlying what's going on with Kubernetes and things like that. We also have some other way of creating the cluster where some people or some engineers want to mention it explicitly. We can do that. Does it work on real data? Let's again try it live. So there was a competition in Kaggle going on some months back. So I'm not going into the details of the competition. It's a regression problem, and it has a bunch of numerical features, and there is a target column to be predicted. So what's the goal of this presentation today? What I want to show is, like, in this demo, I'll be showing that Spark, Fugue, and Ray are working together. as I mentioned in one of the slides that there are 4 steps. So this notebook is a demo of that. And then how we can train a distributed light GBM using Ray on this data set. And this data set was 18 GB, so it is pretty large, reasonably large enough to do some distributed training. It's not too small. And I will show you how things work. So let's look at the data set. It's a Kaggle data set's standard format. Training CSV is there, and there is some sample summation. And so what we do is, so this data set came, and then we loaded that data set, and what I found is like, when I read it, when I'm doing the pre-processing, I'm using Spark to read that data set. And I find that most of the columns are string, which is kind of weird for a numerical challenge. But when I actually see the data set, it's numbers. So what we can do, we can pre-process. So there is no array here still. So that's why I'm not executing this cell. This talk is all about array. So these are all pre-executed. So what we do is we just simple pre-processing, change all the features to float, and drop some of the ID columns which are redundant. We again use Spark to read the data set and use the transform function and then pre-process. And after that, we persist it as a Parquet. So as you can see, that data set is already distributed. Why we do that? Because Ray works very well in a distributed manner. So we need a distributed data set. If I have only one CSV, then it doesn't work well with Ray. It gives no benefit at all. So we have a part, we pre-processed. So now comes the Ray part, the light GBM part. So in Ray, what we need to do is we have to create a function. We have to create a remote function, which will execute on remote machines. And how does that function look like? So this function should look like this. We should be annotating with Ray remote, and it's the training function, which is taking the training files as input. And what does it do? As I mentioned, we read it from Parquet file, shuffling, splitting, training, and validations, normal stuff. And then we repartition based on the number of processes we want to spawn on Ray. And I would like to mention the contribution of Anthony from Ray team. He helped us a lot in giving this into shape. So we repartition the data. So we load it from Parquet. There were 139 files, but then we repartition into 4 actors or 4 processes. And we create Ray D matrix because in order to distribute, we have to use a Ray D matrix. The rest of the part is like normal light GBM. We have a light GBM, we have objective regression, RMSE, and many more parameters. But what is different? The difference is this block. This is the only difference. So we have to use light GBM Ray.train, not light GBM.train. It takes the same things as inputs, parameters, training set, validation sets, and names. No difference. The only difference is this. We have to pass an extra parameter, Ray params, and how many actors I want, and how many CPUs I want to give per actor or per process. So actor is equal to a process. So let's create this method, and then I will try to run it live. So we have actually 139 files. I ran it yesterday. So today I'm spawning a 4-node cluster with 6 CPUs and 4 GB RAM on each CPU. And I also want to wait on the cluster until it dies so that I do not come out of this cell. Last time I showed when I created the cluster, I just checked how it spawned the cluster and it came out. But this time I won't want to do that. So I'm just trying to run it on the fly, live, and see the cluster is nothing is still there. I have only one Ray head node coming up, but I asked for 4. Let's see, yes, I got it. So I got 4 nodes on the fly, and they're running. And since I was fetching the data and then I was doing shuffling in between, so all those things are happening in place right now. So it will be 4 partitions, okay? But just looking at this console output is not very informative. So what we can do, we can go to the Ray dashboard. And we can really see that am I getting all the Ray workers, and am I getting the shuffling across. So I can see there are some reduce operations happening. So Ray dashboard is so critical in monitoring your applications, and then also to figure out that are your CPUs being well used and your RAMs are being well used or not. Based on that, we tweak the size of this cluster, that how much RAM and CPUs we need. So let me see what we are going. So we have spawned 4 machines, and there are 4 ranks, 0 to 3, and everyone is connected, good. And the Ray training is also happening. It is happening so fast, I have to catch up. So here is an example. So the executor is actually spawning up as a process in one of the nodes, and you can verify it live and see that the shuffling you did, do you need 4 partitions, 8 partitions, 12 partitions, based on the number of actors, everything you can figure out from this dashboard. So once this training is done, so what happens? See, this cell is still marked star. The training is done, it has reached the end of its life, but still it's there. Why is it there? The reason it is there because I have said I want to wait on the cluster to die. I don't want to come out of this cell. So that's why the nodes are still terminating, and it's still the cell is still running. So while that is happening, let me show you another quick. We do not have time to do a demo for that. So, but let me. We did a benchmark study. So we ran the same thing on Ray, on Light GBM, and we ran the same program on non-Ray, just a normal Light GBM. So this is the training method, and there is no remote function. Exact same parameters, except we use the Light GBM train. Except we use the Light GBM train call. The rest of the things are remaining same, and we train it. It takes some time to train. So what's the goal of this study? So let's go back to the cluster is gone, everything is gone, so this cell should have come out of its life. Let's go back. Yes, it is done. Okay. So we have, so this shows that we have a clean cluster shutdown also. We just don't keep on head pods and head worker pods hanging around. So we did a benchmark study between this approach and the local Light GBM approach. We persisted 2 serialized models, and we loaded it, and then we did the predictions on the same data set. So what we did, so generally we usually plot residuals of 2 kinds of models, and we see that they are almost pretty similar. And then if we do a distribution of the errors given by these 2 models, they're almost similar. So we were apprehensive that since Ray is working on a partition data set, the model would not be as good as if it was trained on a single machine. So here are some matrix comparisons. I will quickly touch. The Ray accuracy is a little bit lower than the normal Light GBM, which is obvious because the data is already partitioned, and they are using all ring reduce to collect the gradients. But the most important part is like normal training takes 205 seconds, but the Ray training takes 50 seconds. And remember, this 50 seconds includes the time to spawn up the cluster and kill the cluster. The actual training code is even lesser, is very small as compared to these 50 seconds. And we can also calculate the cost. So I'll just quickly touch on, like, okay, we showed some methods, it works seamlessly, but what goes underneath? We are all engineers, we love to see some codes, so I'm not an exception to that. So this is a Ray cluster. So you must have seen this example in the Ray GitHub, and everyone uses that as a starting point. We have some maximum workers, and we have head pods, and Dimitri from Ray team helped us a lot with some cluster queries, and we are not able to spawn our clusters. He helped us a lot. But the bottom line is, like, we want some worker nodes, and I want 3 workers. And this is the YAML you would typically apply if you want to create a cluster. And then you will get the pods and check how the pods is up, and then do a ray init, check ray available resources, and submit the job and shut down. Of course, we can do it, but no data scientist would want to do it. Why they would want to spawn some Kubernetes clusters on the fly? So what can we do? That's where with K8s Ray comes up. So let's look at this code a little bit more. So here is a Python file where, unfortunately, it's not rendering, but we have used in Kubernetes clients to use Jinja templates to apply these YAMLs on the cluster. So it's the same thing. It is just as simple as that. Use some Jinja templates, inject your parameters, how many workers you want, that's done. And you also inject S3 credentials to connect to S3 buckets, K8s confident credentials, EFS mounts, many more things, taints and tolerations for GPUs. Okay, so that ends. I will quickly that ends our talk mostly, and we have some engineering blogs. And if anyone wants to connect with us, please feel free to do so. Thank you so much for your attention.